In part 3 of the notes, I'm going to give you a couple problems where it looks like Newton's method won't work, and then what we need to do to adapt our formula that we found in part 8. So question 11 asks us to find the zero when f of x is equal to x to the 1/3, and we can use our calculators to do this. If we graph, or if we do this algebraically, we end up finding that f of x has a zero at x equals 0. Which means that Newton's method should find that value x equals 0 for us as we are going through and solving. So in question 12, you're asked to find the zeros starting at x equals 0.1 and use 4 iterations of our recursive formula. Remember, if we're going to use our recursive formula, we need to find our derivative of our function. So we have f of x is equal to x to the 1/3. Our derivative, f prime of x, is equal to 1/3 x to the negative 2/3. In solving our iterative formula then, we know that x1 is equal to 0.1, that's given to us. x2 can be found by plugging into Newton's method formula, which would give us our value of x of 0.1 minus f of x, or 0.1 raised to the 1/3, divided by 1/3 times 0.1 to the negative 2/3. And this ends up giving us a solution of negative 0.2. Now, it's not uncommon for us to go from a positive value of 0.1 to a negative value of 0.2. It's possible that our solution could be negative and that we didn't quite have the right value for our starting point. So this is not unusual to see something like this. However, if we go on to x3, I would have to plug in negative 0.2 and then f of negative 0.2 and f prime of negative 0.2 into my calculator. And I'm going to use the calculator to do this, and you should too. It'll speed up the process. And if you do that, we end up getting a solution of 0.4. Now this is starting to look a little bit weird. Remember that Newton's method is supposed to target in on the value of the zero, and it's not doing that here. It started positive and it went negative, which is okay, but then it went back to positive and a larger positive value than what we started with. And we could see when we go to our 4th iteration of this, we end up getting a solution of negative 0.8. So something funny is going wrong when we are working through this. Technically, we need to go one more iteration to solve the problem. It does say 4 iterations, but since x1 is given to us, we should find x5 as well. And now we end up getting a value of positive 1.6. So x is bouncing around, and it's not what we're calling converging. It's not going towards a value. So this is not at all what we expect to happen with Newton's method. Now the reason that this is happening is because of the derivative of our function. So if I were to try to find f prime of 0, meaning the value of the derivative where I know I've got a 0 of my function, I end up getting 1/3 times 0 to the negative 2/3. Remember that negative exponents mean that that value should actually be in the denominator. So I'm getting a 0 in the denominator of my function here for the derivative, and that doesn't give me a solution. This is not a possible value for us. Now, if the Newton's method is supposed to target in on a value for us, this value would have to be defined. So what we need to do is update our rule that we can use Newton's method. We can have xn plus 1 equal xn minus f of xn over f prime of xn, provided that f prime of x exists in all of the places near and especially at our 0. If the derivative does not exist at our 0, then we'll end up getting a situation like we just had. The iterative process will bounce back and forth and we'll get larger and larger values. If it's not defined near our real 0, then we might just need to start with a different value and use that instead, trying not to get that value near our 0 that's undefined at the derivative. Lastly, we have 3 warnings that we need to mention about Newton's method when zeros exist. The first one is that you could potentially pick a value where the slope is equal to 0, and then your tangent line won't necessarily cover the x-axis. So for example, if we've got this x squared function, and you happen to pick the point down at the bottom, you're going to end up getting a tangent line that's horizontal. Well, that line will never cross the x-axis, and you'll never get an updated value for your iterative process, which means you need to pick a new value. So if something funny is going on and you're not getting a new value, or you end up finding some weird things going on, one thing to do is to pick a new starting value. The second potential problem is that you pick a first point that leads to the second point, but then the second point leads back to the first. And what you end up getting is this ping-pong effect where you just keep getting the same values for x1 and x2, x3, x4, x5, x6, etc. So if you notice that the values are just ping-ponging back and forth between the same two numbers, that doesn't mean there's not a 0 in the function. It just means that you need to pick a new starting value. Lastly, Newton's method can only find one 0 at a time. So when we did our very first problem on this, we did x squared minus 7, and we ended up finding this 0 of the function. Well, that was because we started out with a positive value, or a guess, of x equals 1 to start. But there is a second 0 of the function that we didn't actually finish going through and finding. So what you would need to do is pick a guess for x1 that's on the negative side, or at least something that's closer to our second 0, and then you can go through and you can find that value. So you should always make sure to graph your function first. If I ask you to do Newton's method, see how many zeros there are and make sure to find all of them. Newton's method will only find one at a time. It's up to you, the user, to find all of the values.